All right, good morning. So what we'll do today is continue in with chapter 3. Um, on last Thursday, I covered the topics that involve the mole and Avogadro's number because those are important, but also problems that sometimes people have challenges with. But I'm going to go back a little bit here and look at balancing equations. So this is all chapter 3. So really what we covered was section 3.4 on Thursday, but today we'll cover section 3.3, and then we'll move on from there. Okay. So I'm going to start with the idea of balancing chemical equations. Let me write a little bit here. The idea, so this is section 3.3, balancing. So when you take a look, I'm gonna have to pop that off. When you take a look at molecules and compounds, you have these atoms, and one of the rules or one of the laws of science is that matter is neither created nor destroyed in chemical processes in any case. Turns out can be converted into energy. It turns out energy and matter are different manifestations of the same thing in a sense. So matter can be converted into energy and energy can be converted into matter. So it's not strictly true that matter can't be at least lost or gained. It can be lost or gained, but if that's the case, it's transformed into or from energy. So that's actually the idea of nuclear energy, is that what's happening is one atom is transforming into a different type of atom, and in that process, it releases energy. So we'll talk more about energy when we get to chapter 5. But for our purposes here, we'll assume that if you start off with some number of atoms, so these black ones here are carbon atoms, the white ones here are hydrogen atoms, the red one here is an oxygen atom. So if a chemical reaction is occurring, we're not going to lose any of these atoms, they just get rearranged. So for example, that chemical bond might break there, and now you have a new molecule. This molecule right here might then react with another atom, and now you got a new molecule, right? So we're going to take a look at how that plays out in terms of chemical equations. So let's talk a little bit about a chemical equation. So it becomes somewhat burdensome, somewhat burdensome to represent atoms with little balls, right? So for example, I might have that one. Let's do this. Here's another atom. I'll make it another color just to show it as being different in some way. And then here's another atom right there. So a different element, okay? So it becomes burdensome to do calculations with these representations. They're nice to look at, and sometimes we use them. Computational chemists actually like to use these sort of pictures so they can visualize things in their heads. But in a sense, we're going to be doing calculations. So it's more useful to use symbols instead of actual diagrams like this. So the idea then is that essentially we use the symbols of the elements. So, right? So for example, carbon is elements. That's the symbol for it, right? C. Oxygen is O. Hydrogen is H. So there's just 3 of them, right? So we use those symbols to represent the elements. And so if we have a chemical formula, so this is called a chemical formula here. Cool name, chemical formula. So for example, if I have CH4, what this represents is 1 carbon atom and 4 hydrogen atoms. Okay, this is actually the formula, the chemical formula for methane. Okay, so 1. So when it's 1, we don't put a number underneath it. We don't put a subscript. If it's more than 1, then we use a subscript. Okay, so CH4, 1 carbon, 4 hydrogens. And so that would be, you know, something like this. You'd have a carbon atom in the center. And then let's make, I don't know, use green, I guess. And then 4 hydrogens. We'll talk more about structures later, right? So that CH4, what that's doing is it's being used to represent that little picture there, CH4. There's 4 hydrogens attached to the carbon. They're not, it's not that big of a difference in size, but the carbon atom is a little bit bigger than a hydrogen atom. Okay. And then, you know, you could have the same thing, for example, with oxygen, right? So we might have something like O2. Well, O2 is essentially the oxygen that we breathe every day. And it's 2 oxygen atoms that are bound together. By the way, when you have 2, this occurs, interestingly enough, it occurs in nature quite a bit. This is called diatomic. Okay, so oxygen is an example of a diatomic meaning 2 atoms, right? So O2 is a diatomic element. And it's kind of interesting. I'm going to go over the 7 of them in a moment. Okay. Now, what we do is we essentially think of a chemical reaction. We represent a chemical reaction. A reaction is a process that we observe using a chemical equation. Oops, sorry. The chemical equation is, in a sense, the mathematical representation of what's occurring, right? So an example would be, suppose I said, hey, we've got this compound called methane, and it's reacting with this diatomic element, oxygen. Then we would indicate that some process is occurring with an arrow. The arrow is pointing toward what occurs later in time. So you start, so you think of this as sort of your starting point. This is what you start with. And then you're going to end with something new. Now, it turns out that typically, not always, but typically, if you mix those 2 reactants together, you get these 2 products. Now, it's possible to get other products, but this is the most common products that you get. This is actually an example of what's called a combustion reaction, where you take something called a hydrocarbon and react it with oxygen to form carbon dioxide and water, okay? But you can think of it in terms of time. You're, you know, like you start your stopwatch, you're starting with methane and oxygen, and then over time they get transformed, converted into these new materials. So the carbon starts off with hydrogen, but at the end it's now with oxygen. And the oxygen is starting all by itself, right? And then by the end, it's with these new materials. It's with carbon and it's also with hydrogen, right? It turns out oxygen is a very reactive element. It's one of the most reactive elements in the periodic table. It and fluorine are very reactive. And initially, there was very little oxygen in the Earth's atmosphere. Oxygen is so reactive, you just don't tend to find it in planets' atmospheres, not in very much quantities in any case, because it just reacts with other things. So the Earth early on didn't have much oxygen, but then once these cyanobacteria started evolving on the Earth, they started producing oxygen as a byproduct, and that oxygen went off into the atmosphere. It turns out it actually killed off almost all species on Earth. The Earth actually went through a very rough period when photosynthesis started, losing many species, almost all species actually, because that oxygen is so reactive, it just actually tore apart the molecules in these life forms and killed them off. So I think most species that survived went underground, and over time, some of them survive today, but underground. So if you expose them to oxygen, they die. Okay, so let's talk about, so this is our chemical equation right here. And so you got your starting and your ending point. So what we want to do is we want to work on what's called balancing the equation. Okay, so balancing is the idea that you're going to have, because we're not really losing mass or matter, you want to have the same number of atoms for each element on both sides, right? So if you have one carbon on the left, you want to have one on the right. If you have 4 hydrogens on the left, you want to have 4 on the right. Okay, so, that's the process of balancing. So typically what we use in general chemistry is what's called inspection. You just sort of like look at them and then put coefficients in front of the reactants or products to balance them. So you don't use matrix algebra or anything sophisticated. So here's what I'm going to do. I'm going to start on the left side. Typically what I recommend is that you do carbon first, then you do hydrogen, and then you do oxygen. Okay, so carbon, hydrogen, and then oxygen. Okay, and so here's how I'll do it. I'm going to count the number of carbons on both sides. So on the left side, we've got 1, and on the right side, we have 1. So carbon's actually done. That's pretty cool. Carbon's already balanced. So then we go on to the hydrogen atom, and over here, we've got 4 hydrogens. Here we've only got 2, so we have fewer hydrogens on the product side in the water, right? So here's what we do. We use what are called coefficients. Okay, the coefficient, it's a mathematical term, right? So in algebra, you learn about this, right? Like ax squared plus bx plus c equals 0, for example. The a and the b and the c are called coefficients. And those coefficients go in front of the variable, right? Well, same thing here. You can think of the CH4, the symbols, and O2 and CO2 and H2O. Those compounds, those reactants and products, think of them as the variables x. So you put coefficients in front of them. So if I were to say, look, a equals 3, then what that means is you have 3x squared, right? Same thing here. So what I'm going to do is I'm going to say, okay, this is 4 for the hydrogen, but I want to have the same number of hydrogens on both sides. So what I'm going to do is I'm going to say, what could I put in front of the water as a coefficient that would make it so that that number times this number here, which is called a subscript, is equal to the number that we have over here, which is 4, right? So what times 2 is equal to 4? Well, that's pretty clear. It's pretty 2, right? It's 2 times 2 is 4. So the physical meaning of this, when you put a coefficient, is that you have that many of them. So you have 2 waters, right? And so the idea is that if you have 2 waters, each one has 2 hydrogens, so that would be 4, right? And so now this 2 here times that 2 there, that's going to give you a 4. So you now have 4 hydrogens. So you have the same number of hydrogens on both sides. So now I can check off the hydrogen. Now keep in mind that by putting that 2 as a coefficient in front of the water, that changes the number of oxygens in the water as well. This coefficient refers to everything in here. So just like in algebra, if I said, 2xy, well, that 2 is telling you how many x's you have, but it's also telling you how many y's you have. So the same thing here, this 2 is affecting the hydrogen and the oxygen. So what do we do there? Well, let's count up our oxygens. We have a subscript there, 2. So we have 2 oxygens on that side. We have a subscript there, so we have 2 oxygens on that side. But we also have the 2 here, right? 2 times 1, so that's 2. So actually, in terms of oxygens, we have 4 oxygens on the right side. So now we do the same thing. We want the number on this side to be equal to the number on that side, but the number on this side is larger. It's 4, 2 plus 2. So same idea. What could we put as a coefficient so that that coefficient times 2 is equal to your 4? And that would be a 2 again, right? A lot of times these numbers are small, like 2, 3, 4, sometimes 5 or 6, but usually not. So now let's just kind of go over this. 2 times 2 is 4, right? Why is it 4? Well, because really what you're saying is you have an O2. That's what that O2 means. And then, but you've got 2 of them. It's how many of those O2s you have. So that's 1, 2, 3, 4 atoms. Over here, you've got 2 atoms here. You've got 2 atoms here. So that's 4. So now it's balanced. So again, when you see this kind of setup where you have what's called a hydrocarbon, and it's reacting with oxygen, generally I recommend doing carbon first, then hydrogen, and then oxygen, and that will generally work pretty well. Now, this one is a relatively simple one. There's a group of them that require an extra step, so I'll show you one of those next, okay? It is now balanced. There are now the same number of atoms on both sides. Now, keep in mind that a common mistake is to change the number on the subscript. We don't want to do that. So, for example, when it comes to the hydrogen, we could have put CH2. That would give us 2 hydrogens, but that doesn't work. And the reason it doesn't work is that if you put CH2, let me see if I can show you that. Oh, there we go, CH2. That is a different substance than CH4. It's chemically a different material. CH4 has 4 hydrogens. So it's kind of like turning a dog into a cat, you know, or a bird into a dog. You can't say, hey, I've got 1 dog, now I want to make it a cat so that everything balances out. So CH4 has got to remain as CH4. But what you can do is you can change how many of them you have, how much CH4 you have, or how much H2O you have, or how much CO2, or how much O2, and that would work. Let me show you another one here. This one's going to be a little bit more complicated. Yeah, go ahead.
Can I ask a quick question? I don't know if you want to like, I'm sorry, I just woke up like 10 minutes ago. I haven't gotten used to talking yet. After you do this example, if you have a few minutes, can you address the difference between the molarity value and then the number of atoms value? Or just because like sometimes when the book does it or when Alex does it or they ask us to show our work, they will, when they total up the number of atoms, they'll address it as like moles. And I don't know if for our purposes, we're supposed to understand the difference or if we can just treat them as interchangeable.
Okay, we'll take a look at that next after.
Yeah,
okay.
thank you.
Okay, so now let's try another. This one again is another combustion. So this one is going to be, you know, ethane, which is C2H6, reacts with oxygen to form carbon dioxide and water. So what you want to do is you want to balance the equation. Okay, so notice it says with oxygen. So this is, I'm going to bring up this point right here. The idea is that there are, in nature, there are certain elements that are what are called diatomic. Okay, there's 7 of them. Hydrogen is one of them. So if you see a problem where they don't give you the chemical formula, but they say that hydrogen reacts with, or hydrogen is produced by, you want to write it as H2. It's called a diatomic element. And that's just, you know, we'll get in, when we get into chemical bonding later in the semester, we'll see why it's H2 and not just H. But there are 7 of these diatomic elements. Nitrogen is the second one. So if the problems, typically most of these problems, they'll give you the chemical formula. But if they say nitrogen, you know, balance the equation between nitrogen and hydrogen to form ammonia. Then if it says hydrogen and nitrogen, then it would be H2 and N2. Oxygen also. Okay, so it's those 3. And then I'm going to write them off to the right here because the other 4 are in the same column. These are what are called halogens. I'm sorry, I put Fe. I meant to put F2. There we go. Chlorine, bromine, I'm sorry, bromine. Getting ahead of myself. Br2, sorry. And then iodine. Okay, so those 4, they're in group 7A of the periodic table. And they're all, they're all the same. They all behave the same way in this sense that they form diatomics. Iodine is what you find in like iodine antibiotic stuff. Bromine you don't see very often, but it's in the ocean. Chlorine, right? Chlorine and then fluorine, right? So it's hydrogen, nitrogen, oxygen, and then the halogens, which are group 7A. So let's take a look at this. It says ethane reacts with oxygen. So that means we would write C2H6 plus O2. So notice when it says reacts with, you write a plus sign, a plus symbol, to indicate that these are two things that are reacting with each other, two separate substances. So we're mixing them together, right? Like imagine you're baking a cake, right? You put the flour in, you put the sugar in, you put the eggs in. The ethane is like the flour and the oxygen is like the sugar. You're mixing those two separate substances together, then they're going to react. To form is just a way of saying they're going to produce. You're going to get products out of that. That's telling you it's a chemical reaction. So they form carbon dioxide. Carbon dioxide, carbon. Di means two. So dioxygen, dioxide. So that's carbon dioxide. And so when it says and, that's another way of just saying plus. Separate substance. Water is H2O. I assume everybody knows water. So there you go. So there's the chemical equation. You're almost there. Now you just have to balance it, right? So it says here, balance the chemical or balance the equation, okay? So same idea. I would recommend you do carbon first, then hydrogen, then oxygen. This one's a little trickier because what ends up happening is you get a fraction. And so it's just an issue of dealing with fractions, but that's not that big of an issue, okay? So let's start with the carbon. We have two carbons on the left, but we only have one on the right. So the idea is you're going to put a coefficient on the smaller one, right? This is smaller than this one, so that they're equal. So if you have two on the left and you have one on the right, you put a 2 here. So now 2 is equal to 2. So now you've put a coefficient. So now you got 2. Now keep in mind, now that means you have 4 oxygens, right? Because 2 times 2 is 4. Now hydrogen would be the second element. There's 6 of them over here. There's 2 of them over here. Okay, well, same idea. Some coefficient times 2 has got to equal to 6. Well, you just go through your math tables, right? What times 2 is 6? 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. So put a 3 there, right? Now you got 6. Okay, now, again, that changes the oxygen. Now you got 3 oxygens over here, right? 3 H2O, so 3 times 1. Remember, if nothing's written here, it's really a 1. Okay, so now let's do our oxygens. We've got 2 over here. So we have 2 on the left side, but on the right side, we've got 4 plus 3, so we've got 7. So I'm actually going to write that down here. We've got 2 here, and then we got 7. So how do we deal with that? Well, this is the smaller number over here, right? 2 is smaller than 7. So just use your algebraic skills. Here's what you can do. You don't know what this number is going to be, but I'm just going to write it as n. It's going to be something, right? So what you can do is you can say 2 times n, so 2n, is got to be equal to the larger number, which is 7, right? Those numbers have to be equal. We have to have 7 on both sides. So here's what you do. 2n equals 7. Okay, well, 2n equals 7. So what's n equal to? You just divide both sides by 2, and you get n equals 7/2. And that is actually correct. If you have 7/2 CO2, I'm sorry. If you have 7/2 O2, that actually works out. You can check it. 7/2 times 2 is 7. 2 times 2 is 4. 3 times 1 is 3. 4 plus 3 is 7. So it actually works out. But notice you have a fraction here. The coefficient is a fraction. Now, strictly speaking, there is nothing wrong with having a fraction in a balanced equation, except for the fact that people who write textbooks in general chemistry And people that write software in general chemistry, like Alex, for some reason, they don't like fractions. And I'm not sure why that's the case. But it turns out chemists use fractions all the time for coefficients. But in any case, since you're doing your homework on Alex, you kind of want to get the right answer and you don't want to get frustrated by Alex. So there's one more step to resolve that issue. And that is to eliminate the fraction and make everything whole numbers, okay? To some extent, I think part of the reason that fractions are typically avoided in these is because people would write multiple choice exams. And so typically what in a multiple choice exam, what you would say is, what's the coefficient in front of oxygen in the balanced equation? And you would write A is 1, B is 2, C is 3, D is 4. And so you wanted to have whole numbers in the answer. So in any case, here's how you get rid of it. Algebraically, think of it this way. Suppose I said, you know, y equals 7/2 x. Well, no, let's make it a half. Make it a little simpler. And I said, I want to know, you know, manipulate this equation so that x equals something. Not 1/2 x equals something, but x equals something. What you would do is you would multiply everything by 2. And you get 2y equals 2 times 1/2 is 1, and you get x. So now you've answered your question, right? We're going to do something very similar to that here. To eliminate the fraction, to eliminate the half, we're just going to multiply everything by the smallest number possible to eliminate it. So what I'm going to do is I'm going to rewrite the equation here. And I'm going to multiply everything by the smallest number I can to get rid of the fraction. And the smallest number you can multiply to get rid of a half is a 2, right? I mean, multiplying by 4 would get rid of the fraction too, because 4 divided by 2 is 2. But we want to use the smallest possible. So I'm going to multiply everything by 2. So you get 2C2H6. 7/2 times 2 is 7. And then that's a 4, right? 4 CO2. And then that's a 6. 3 times 2 is 6. Okay? So if when you balance the equation, you end up with a fraction, typically that fraction is a half, a factor of a half, like 3/2, 5/2, 7/2, 9/2. Just multiply everything by 2. If it turns out that you had to make it a third, like if it was 7/3, then you just multiply everything by 3. And keep in mind, since you're multiplying everything by the same number, in this case 2, it's still going to be balanced at the end. It was balanced, it's still balanced. You can check it. 2 times 2 is 4, so there's 4 carbons. There's 4 carbons. 2 times 6 is 12, so there's 12 hydrogens. 6 times 2 is 12, so there's 12 hydrogens. And the oxygens are still balanced too. 7 times 2 is 14. 4 times 2 is 8. 6 times 1 is 6, so that's also with 8 plus 6 is 14. So it's also 14. So it's all balanced. Okay. And there you go. That works pretty well. Before we go to your question, Sophia, does anybody have a question on this, what I just did there? Okay. I want to show one more example just so that I can give you another example that's in Alex. So the example in Alex has to do with something that's not a combustion. It doesn't have carbon and hydrogen and oxygen. So let me show you one more. And for this one, this is what we would call an inorganic reaction because there's no carbon and hydrogen. In this one, they give you bromine and iodine. And they do put the states of matter in there. So let me just remind you that when you see in parentheses after an L, that means it's a liquid. So they're telling you the state of matter. Because it turns out things react differently if they're solids, liquids, or gases. Sometimes they won't react unless they're a particular state, but it tells you some information about it. S is solid, so that's telling you it's a solid. And then G is telling you it's a gas. We'll see one more in the next chapter, which is AQ, which is aqueous. Okay. All right. So here it is. This one's a little bit different. Notice there's only one product. This is what's called a combination reaction. When you're combining two things to make one thing, that's called combination, as opposed to the previous one, which was combustion. Okay. In fact, this is interesting because all three states of matter, solid, liquid, and gas, are represented in it. Okay. So same idea, but in this case, it's not three elements, it's only two. So in a sense, it's simpler. So here's what I would do. Just, you've got two elements here. So you got bromine and then you got iodine. So those are your two elements. You got to balance each of those. In a sense, it doesn't matter which one you do first here. It's up to you how you want to do it, but let's take a look. So I'll start with the bromine first. Now we have a little tricky situation here. See how there's two there and there's three there? Okay, so this is a little bit like the previous one. So what I'm going to do is this one's smaller, right? 2 is smaller than 3. 2 is less than 3. So I want to multiply that 2 by something to make it larger. Okay, now mathematically, you could take the one that's larger and multiply it by something to make it smaller. There is a number you could multiply by 3 to give you 2. You could do it that way. But generally, people feel more comfortable going up, making bigger numbers as opposed to making smaller numbers. So what do I have to multiply 2 by for the bromine in order to get 3? So there's some number here I got to multiply that by. So N times 2, right? Don't forget the coefficient there. Subscript. So N times 2, we want that to equal the larger number on the other side, which is 3, right? So just divide both sides by 2. 2 over 2 is 1. You get 3 halves. So that means we want to multiply the bromine by 3 halves. Okay. Now the bromine is done, right? Again, it is a fraction, and so that may need to get resolved in order to enter it. If you were doing this in my classroom, you would be taking an exam where you would just write out your work, and I would accept the fractions, but you can't really work that on Alex. So now let's do the iodine. Iodine's a little simpler, right? Because over here it's a 1, and over here it's a 2. That's mathematically simpler. You just put a 2 in front of that, right? But notice what that did. By putting that 2 in front of the iodine, that gave us 6 bromines. It changed the number of bromines. So now what we have to do is just say, okay, well, what are we going to do about the bromine? Okay, the iodine's done, but now the bromine's no longer done. Okay, so what I'm going to do is I'm going to say, okay, well, let's see what's going on here. We have 6 here, right? 2 times 3 is 6 bromines. So that means we need to have 6 over here. So what I'm going to do is I'm going to get rid of that coefficient because it's no longer going to give me 6. And I'm just going to say, well, if I want 6 over here, what do I have to put in front of it? Well, 2 times 2 is 4. 2 times 3 is 6. So a 3 will work. Okay. So now we've got 6 bromines. And we've got 6 bromines. We've got 2 iodines, and we've got 2 iodines. So now we've got a balanced equation. Okay. So that works. Now, suppose I had done the iodine first. Suppose I'd done the iodine first. Okay, I got 2 over here, so I'll put a 2 there. That gives me 2 on both sides. Now I've got 6 bromines over here, so I need a number in front of the 2, a 3. So see, it actually would have been faster to do the iodine first and then the bromine. But sometimes it's not easy to see that would have been the case. So if you happen to pick iodine first, you maybe did it more simply. But if you happen to pick the bromine first, it took a little bit more work, but that's perfectly fine. You still get the right answer. You just have to do an extra step there. Okay. So that's another type. So they have you do combustion, they have you do a combination, and then that's pretty much it. Are those 2. Okay, let's see, anything else here? I'm looking through here. I'm just scrolling through the Alex problems just to see if there's any that are significantly different. It doesn't look like they are. Those are pretty much the types of problems that you'll see. Okay. All right. Good. So that's balancing equation. That's section 3.3. Okay, Sophia, let's go back to your question then.
Yeah.
So what, can you give us some more specifics about what you're talking about?
So just when I saw, not specifically in the balancing equation section, but it was just a little bit later, but it relates back to, being able to kind of count the number of atoms in these.
Counting atoms, is that what it was?
Yeah. So it's using units as moles. And it relates back directly to this because you have whatever coefficient in front of the actual chemical symbol for this element. So let's say you have O2 and you have like 3O2. So it's saying there's 6 moles of oxygen. And I just kind of want to understand how it's using that. Yeah, so exactly. So for something like that, so you would have, if you're trying to show for.
So this one's not going to ask for
like
moles.
aluminum.
Yeah.
Or, no, not aluminum. Let's say you have, oh my gosh, hydrogen. Okay, hydrogen in the reactant side. So it would convert that to 36 hydrogen, right? And I'm just trying to understand what's the difference between when we're counting atoms and when we're counting molarity. And if we could kind of, do we really need to understand the difference, or for our purposes, can we just treat them interchangeable?
Good. So there's three concepts you just discussed right there. The first was counting with atoms, number of atoms. The second was moles, and then the third was molarity. So let's keep those in, or put them into perspective.
Yes, perfect, because I am confused between the difference between all of
so molarity is in chapter 4, and molarity has to do with what we call concentration. So if they ask for concentration, that's when you would deal with molarity. Okay, that's not covered at all in chapter 3. Okay, so not molarity. Moles, typically, moles are dealt with when you're given the grams of a substance. So if you're measuring out water and you measure out 5 grams or 50 grams, that's when you're going to deal with moles. Counting the actual number of atoms is, in a sense, a relatively rare thing that we do in chemistry. It's relatively rare that we count the number of atoms. It does happen. People do it. So people, in atmospheric chemistry, they might actually count the number of oxygen atoms or ozone molecules in a given volume of air. But it's a relatively uncommon question. However, because this is an introductory course and we're kind of learning about atoms and moles and all of that kind of stuff, you do see problems where they ask you for the number of atoms. So this is where sometimes reading the question very carefully can help you kind of direct yourself where you want to go. So let's take a look at this one here. See how it says, what is the total number of oxygen atoms in the chemical equation? Okay. So notice they don't give you anything about mass in there. There's no like 5 grams of this or 50 kilograms of that. So if they don't give you any mass information and they're asking you for how many atoms are in this equation, right? Then all you got to do is just count up with these numbers. You don't have to use Avogadro's number. You don't have to use moles or any of that kind of stuff.
I see. So for an answer like that, you would just put like 38 atoms. You wouldn't put 38 M or anything.
You got it. Just yeah, exactly.
Okay.
And so for example, let's say in this one is oxygen. So let's look at oxygen. So this is, I mean, it's not real complicated, but there's a little bit of effort into it, right? So the first thing we would do is we'd say, okay, well, here's oxygen on the left side. That's not the right side. Here's oxygen on the left side. We want the right side. Now, they use left, right. I might use reactant side, product side, but whatever. So on the right side of the equation, it looks like there's some oxygen here. It doesn't look like there's any over here though, right? But the way they kind of wrote this is kind of, interesting, right? So here's the idea for the oxygen on the right side. You've got OH parentheses 4. When something is in parentheses and then there's a subscript after it, the subscript refers to everything in the parentheses. So it refers to the O and the H. And that kind of makes sense to do it that way, because if you didn't put the parentheses there, you might think it was just the 4 was just referring to the hydrogen. So you've got 4 oxygens in the parentheses there. However, the coefficient, it refers to everything in that substance until you get up to the plus sign, right? So 8 of sodium, of aluminum, and of O and of H. So really you've got 8 OHs, so 8 O's, but then you got 4 O's in one, in that group there. So it's really 8 times 4, which would be 8 times 4 is what, 32? So it looks like there's 32 there. Now, is this a balanced equation? It doesn't actually look like it's balanced, right? Because you've got, maybe it is, because you've got 18 oxygens there. So 18 plus another 5, right? 5 refers to everything after here. So 18 plus 5 is 23, plus another 9. 3 times 3 is 9. So it actually works out to 32 on both sides. So it is actually a balanced equation. Okay. So yeah, if they had told you in this question, hey, we've got, 5 grams of NaOH, how many moles is that? Then that's a very different type of question. That's where we're going to have to, do a mass to mole conversion and all that stuff. That comes up later, but that's how you would see that. Okay. Now, if you take a look at the explanation, their explanations will often be a little bit different from mine. And sometimes they leave steps out, little details here and there. But if you take a look at it, really when they go through the explanation, they're saying, look, we're just counting up the number of atoms here. So it's going to work out to be like 32. Okay. Does that make sense?
Yes, it does. It might be later, and this is beyond the scope of this lecture, so I don't want to take up too much time, but it's like it gets into things like with rate law later, and that's when, I don't know, you start using coefficients.
That's the other course. That's the other course you're taking.
Right. I just wasn't sure, for this, for this particular course, what the difference was between these concepts. But I think actually that really helps. So molarity refers to concentration. Moles is when you're doing conversions between grams and moles and stuff like that. And then atoms is a very sort of introductory kind of specifically counting the number of atoms in the equation.
Right. And the mole is powerful. It's actually one of the 7 basic units in the International System of Units because it's useful. The mole is very useful as just sort of accounting how many you have. So that 6.02214, whatever it is, times 10 to the 23rd is a mole. That ends up being pretty useful. Okay, so let's take a look then.
Thank you.
Let's take a look at one more. Let's see. Yeah, let's take a look at one more. So this is one more Alexson balance. I want to really kind of show you one more balancing chemical equations here. This is where they ask you to do it from the description of the reaction. So this is what's called, actually, let me show you just real quick, just so you can kind of see this. Writing a chemical equation from the description of the reaction. So this is, in a sense, for first semester chemistry, the most sophisticated or complex of the balancing chemical equation problems. Because not only are you asked to balance the equation, they don't give you the equation, they give you the words that describe the reaction, but you have to come up with the formulas and then do the balancing. So in this example, it says, we're not going to give you real complicated ones, of course. This one says that nitrogen monoxide gas is formed from or by the reaction of nitrogen gas and oxygen gas. And then you want to write the balanced chemical equation for the reaction. Now, when I do this, I'm going to write the states of matter because they give us the states of matter for everything. Everything in here is a gas, so we can write G. But keep in mind, notice that you've got nitrogen. That's one of those 7 diatomic elements. And you have oxygen, which is another of the diatomic elements. So in some of these, they're going to give you the diatomic elements on purpose so that you know the context of when to write those in. Okay, so nitrogen monoxide, that's a relatively simple compound. Nitrogen is N. Now what's mo mean? Mo, it's really mono. Mono means 1. Di is 2. Tri is 3. Tetra is 4. Penta is 5. So nitrogen monoxide, 1 oxygen. So it's just NO. Okay. So, and they also, in a way, the way they wrote this is they didn't write, nitrogen plus oxygen reacts to form. They actually put the reactants at the end, right? They said nitrogen monoxide gas is formed. So that's the product. So that's going to be on the right side. And then the nitrogen and oxygen, even though they put the words last, they actually go in the front. They're on the left side, just the nature of language, right? So let's take a look at this. Let me share this. Okay, so, I'll write it this way. Nitrogen monoxide gas. Okay, so that's your product over there. It's formed, produced. And then it's being formed from nitrogen gas and oxygen gas. Okay, so those are your reactants. Okay, the arrow points towards the products. Technically speaking, there's nothing wrong with doing it this way. You could, in theory, write it this way. I don't think Alex would like it because they're pretty strict. But, it's actually it's following the rules. There isn't actually a rule left side, right side. The rule is what direction does the arrow point? So in this case, the arrow is pointing towards NOs, and so that's the product. So this would actually be okay. But this is probably the more preferred way. You write the reactants on the left side and the products on the right. Okay, so now you can balance it, right? So let me write it again. N2, O2, and then that gives you NO. Okay. All right, so let's start. Again, you have 2 elements. You have nitrogen and you have oxygen. Okay, so it probably doesn't matter which one you do first in this case. If you're doing a combustion, do carbon, then hydrogen, and oxygen. But for other reactions, it's sort of up to you. So I'll do the nitrogen first. It's the first element that appears in the equation. There's 2 there. So I'll put a 2 over here, right? 2 times 1 is 2. That's balanced. But look what that did. That actually also balanced the oxygen because there's 2 oxygens here, but now there's 2 oxygens there. So that's actually balanced too. So sometimes that'll happen. Balancing one will balance the other. Okay. By the way, there are some equations that are balanced where everything's a 1. So for example, you don't have to do anything to that one. It's got 1 carbon on both sides and it has 2 oxygens on both sides. That's kind of a freebie, right? That's kind of cool, but that happens sometimes too. So there's your balanced equation. The prefixes, if you're running into problems with these prefixes, so mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca, like a decade, is 10. So for example, let me just erase this. If you had something like dinitrogen pentaoxide, sometimes people will drop off the first vowel, so it might just be called pentoxide. but pentoxide or pentaoxide. Di is 2 nitrogen, so N2. Penta is 5 oxygen, so O5. So dinitrogen pentoxide or pentaoxide would be N2O5. When you have 2 O's in a row, they always knock off one of the O's. So you wouldn't have monooxide. You would just drop one of the O's and it would be monoxide. Okay, and there you go. So that's writing a chemical equation from a description of the reaction. And these are relatively simple equations. They're not having you do real ones. I mean, real difficult ones. Looks pretty good. So you may, you're going to want to probably have a periodic table around nearby while you're doing these. I find it useful to get a periodic table that has the names of the elements so that you can look these things up pretty quickly. And then that'll help you get through some of those problems and get practice with them. Okay. Let's see. Okay, I'm going to go back to 3.4. We did a bunch of 3.4 last Thursday, but we didn't really do every type of problem. So I'm going to do at least one more. Okay, so let's look at calculating. So this is going back to section 3.4. Okay. And we're going to, what I'm going to do here is I'm going to help you just sort of do calculating molar mass. Okay, from the chemical formula. So here's an example where they give you CH3OCH3. And they ask you to find the molar mass. Can you calculate the molar mass for this particular compound? So it's very, it's very simple, really, quite frankly. All you do is you look up the elements. So here's carbon. So you look up carbon. Let me just bring this up so I can see if I'm doing it. So carbon, the number you want to use is down here. Now, sometimes people call this the atomic mass, but sometimes they call it the molar mass. It just depends on the context. If you're doing molar mass calculations, that's the molar mass of carbon. The second element I see in here is a hydrogen. Okay, so there's your molar mass down there. And then the third element I see in here is an oxygen. And again, sometimes these are represented with more significant figures. So for example, oxygen might be 15.9994, hydrogen might be 1.0794, and carbon might be 12.0107. There's just depends how many they're putting in that table. Okay. So there you go. So what you do is you count everything up. It looks like there's one carbon here and there's another carbon there. So you got 2 carbons. Actually, let's write it this way. Carbon, hydrogen, oxygen. So here's your number. So there's 2. You've got 3 hydrogens here, but another 3 there. So that's 6. And then you've just got 1 oxygen there. Okay. So what you do to find the molar mass is you just add up the mass of every atom in the molecule. So if you've got 2 carbons, you would multiply that by the molar mass. Because this is how much 1 mole of carbon weighs. But we have 2 moles here. Okay, so 2 times 12.01. For hydrogen, 6 times 1.01. And then for oxygen, 1 times 16.00. Okay, the units of molar mass are grams divided by moles. It's really how much something weighs in the units of grams, which is a common unit, per given mole. So if they're asking you for the molar mass, that's what you'll do. So if you add these up, you get, for the carbon, you get 24.02, right? 2 times 12.01. For the hydrogen, it's 6.06 because it's 6 times 1.01. And then for the oxygen, it's 1 times 16, so 16.00. And then you just add them up. And so you have an 8 here, you have a 0 here, you have 12 plus 4 is 16, and then 2 plus 1 plus 1 is 4. And then again, the grams per mole is the units. Okay. And then we talked about this on Thursday, that you can use the molar mass as a conversion factor because we can write it this way. For this particular compound, which is, I think, it's methyl ether, dimethyl ether. That's how many grams is equal to 1 mole of this CH3OCH3. That would be the molar mass. So that means that if you're going from moles to grams or grams to moles, you can use that as a conversion factor. Okay. So that's calculating the molar mass. I'm just going to look and see if there's anywhere they give you kind of more complicated formulas. Let's see. Well, that's interesting. Oh, let's look at this one. So here's another one. Again, finding the molar mass from the chemical formula. All right, so it's in this way, it's actually very similar to the one we just did. It's a similar type of compound. But what they're doing is they're representing it in a different kind of format. See how that's written a little bit different? This is really, okay, let me show you what this is. See how there's a 2 there? You got CH3, CH2 in parentheses, and a 2, and then the O. Really what they're doing is they're just representing what we just did. This is not the same molecule, but it's similar. They're just representing it differently. They're doing that. So they're representing this. And you'll see that a lot in chemistry. We represent things differently. These, that's what that means, essentially. Now, you don't have to have it in this form to do the problem, but I just want to show you that that's really what they're saying. This in parentheses is a group, so CH3, CH2. There's 2 of them, and then there's an oxygen. So really, it's 1 on either side. But again, you don't need to have it in this form. You can do it in this form, but be aware of the notation. If you count up the number of carbons, hydrogens, and oxygens, let's be careful. You've got 1 carbon here and another, so that's 2, but they're in the parentheses, so that's 2 of them, 2 times 2, so it's really 4 carbons. The hydrogen, you've got 3 here and 2 here, that's 5, but there's 2 of those groups, so that's 5 times 2, so that's 10, but the oxygen's not in the parentheses, so there's only 1. So 4 times the molar mass of carbon, 10 times the molar mass of hydrogen, 1 times the molar mass of oxygen. So that gives you 48.04, 10.10, and 16.00. Then you just add them up. 4, 1, 14, what is that? 7. And then again, the units are grams per mole. Okay, so 74.17. 74.14. You get the same thing if you did it this way, right? You'd have 1, 2, 3, 4 carbons, 5 hydrogens, another 5 hydrogens, which is 10, and then 1 oxygen. So everything in the parentheses multiplied by that subscript there. Okay, and that's the molar mass. Again, what that means is 1 mole of this compound, CH3CH2 2O, has a mass of 74.14 grams. Okay, that's how much it weighs. That's its molar mass. Okay. So there you go. So those are the 2 problems. So we did our 3.3, which is chemical equations, and we did a little bit more of 3.4. We still have 3.5, 3.6, and 3.7 to do. So this is what I'm going to do, just so you know. Technically tomorrow, Wednesday, is a holiday, right? It's a holiday. So is Thursday. So the college is actually not holding classes Wednesday or Thursday. But what I am going to do is I'm going to go ahead and I'm going to do a 9:30 to 10:30 lecture both days on Wednesday and Thursday. And of course, it's optional. It's always optional. Coming to these lectures is optional for you. But I will post them to YouTube so that you have these to work over the weekend and into next week. So those lectures will be there for you. They are, in a sense, already from the previous semesters, but I want to show you every semester is a little bit different, and I tweak things a bit, so they're a little different. So I will start working on section 3.5 and 3.6 on Wednesday and Thursday, and then that will lead us into, continuing on. Okay, so have a great day. This will be posted, and have a great holiday, and then have a great weekend, everybody.
Thank you, Professor. Thank you.
Thank you so much.
Very
Professor, can I ask a question?
sure. Let me just stop the recording here.